Hi, I'm Chandler. This is my heat transfer final project on the heating of a room with an open window. The purpose of the model is to inform the design of a temperature-sensitive casement window, which uses a gear system coupled to a DC motor controlled by temperature to open and close a window and regulate temperature in a room. Our problem statement is how and where to measure temperature input, since it is time and space dependent, so we will evaluate time and space dependent temperatures and heat flows to vary the location, temperature sensor, and make the system easier to adapt with simpler circuitry and a versatile temperature measurement location. Our background heat transfer theory involves convective and conductive heat transfers. Convective heat transfers come from internal force flow through an open window, external force flow over the isothermal plate of the back wall, and natural flow over a cold plate considered as a floor. Conductive heat transfer is done by a temperature difference between walls composed of siding, wooden insulation, and drywall. These are combined into resistance values here, and overall heat transfer coefficients are evaluated from this to used in all solution methods. Our solution methods are a transient and steady state 1D analytical model, as well as a 3D finite element analysis. Our transient model uses a lumped approximation, a one-term approximation, and a high-chart solution. We assume here that the wall behaves as a multi-layer plane wall. Heat flows in the front and the back halves are independent, and ambient temperature and wind speed remain constant. The steady state model uses an ODE solution for the heat transfer equation, a resistance model, and a shape factor solution. Assumptions for the steady state model are that heat equation equals 0, constant temperature in the center of the room and at the walls, uniform wind speed, and heat flows in back and front halves remain independent. Our 3D finite element analysis uses ANSYS transient thermal to model a room with convective heat transfer on the front and the back walls and inside with initial and ambient temperatures. So here are our temperature results from that, and here are heat flow results where the outside of the room gets hotter than the inside of the room, and there's obviously more heat flow along the outside of the room. So our lumped approximation lumps the front and the back halves of the wall as expected. Temperature plots are as expected, but heat flows do not match due to the inaccuracy of a lumped model and also the fact that this room does not fit typical lumped criteria of a single object between two temperatures. Our high-chart solution is used for the front half of the room at the wall surface, the midpoint between the wall surface and the center of the room, and at the center of the room. The front surface and midpoint behave as expected, where the center of the room does not fit the highest correlation since it has a different initial temperature than the outside of the room. Similar trends can be expected for the back of the room. We found the one-term approximation to be the best method. Zeta and C values were used to find theta values for 5 points in the room, and results remained consistent on the logarithmic path for temperatures and heat flows. We did a parametric study of varying wind speed for our 1D analytical models. In the transient results, our temperature plots spread apart because the front half of the room is much more affected by the increase in wind speed than the back half of the room due to its direct relation with internal force flow through the window. Our steady state results are that temperatures near the walls increase with higher wind speeds, but this introduces inaccuracies near the boundary conditions. For example, an artificially large heat flow is needed with a high wind speed to maintain the 10 degrees Celsius in the middle of the room, whereas it's much lower with lower wind speeds, meaning this model is more effective for lower wind speeds. Our conclusion is that the 1D transient model using one-term approximation provide the most accurate overview of this situation, and temperatures and heat flows vary most near the heat sources and follow logarithmic trends. These trends can be used to move the temperature probe in the casement window to the wall of the room rather than using the location where it is to be regulated while still retaining the accuracy by accounting for the delay in temperature increase between the wall and the point where it's to be regulated.